那要缴多少？一天要多少钱？
天要700港币。
那还蛮贵的。
啊，是啊。
天哪！那要缴多？
这个声音怎么样？有没有什么回音之类的？
还好没有。
对。
Maybe I can introduce you. And
also okay.
Well, welcome everyone. Welcome to Harvard CMSA Quantum Matter in Math and Physics seminar series. Today, I'm very honored to introduce my academic brother, actually, Tian Lan, or Lan Tian. He studied at the Parameter Institute and also University of Waterloo, where we overlap when I visit PI Parameter Institute. And he was supervised by Professor Xiaogang Wen. And then he continued to did his postdoc at the U Waterloo, and currently starts his professorship at the University of Hong Kong, as a CUHK, Chinese University of Hong Kong. And his topic today will be higher dimensional topological order, higher category, and classification in 3+1 dimensions. So we should welcome the audience. If you have questions, and feel free to either just raise your hands, or if you find appropriate, you can just directly speak up, or you can also type in the chat. So let's welcome Tian. Please take over.
Okay, thanks for the introduction, and thanks for this invitation to talk here. Since I'm in the hotel for the quarantine purpose, so if my internet or the sound is or the video is not very good, please forgive me. Okay. So today let me talk about this classification of three-dimensional topological order. And as Drew asked me to go slowly, I'll try my best to explain as more details as possible. So if you feel something is too fast or you have questions, feel free to interrupt me. Thank you.
Oh, I should also mention one thing. I think Teal Johnson-Fried will be giving another talk related topics next week, so everyone should stay tuned, and there will be a related talks next week.
Yeah.
Thanks. Great.
Okay, so this work was done in collaboration with Kong Liang and Professor Wen. Actually, it's kind of some not very recent work, and as Drew mentioned, Theo actually has some new progress on this direction. And he had some more rigorous definition and proofs, and I think Theo is going to talk about those next week. Okay. So before we start, I have some like working definitions because at the time we did this, we don't have a rigorous definition. So the working definition will be we view topological orders are just quantum gapped quantum liquid states without any symmetry. In particular, we'll focus on the topological defects or topological excitations, or in some maybe other authors will say the extended operators, extended objects, things like that. And like a basic assumption is that if we exhaust all the properties of those topological excitations, they can determine the topological phase up to the invertible ones. And the invertible is defined with respect to the stacking of the phases. Okay, and by topological defects, I mean the gapped defects whose physical observables, whose properties only depends on their topology. So I mean there is no dependence on the matrix, on the scales, or like on the symmetry or other things. And in particular, when I say excitation, I will just mean some special defects, the defects between the trivial defects. And trivial defects just means there's no defect. And the defects between no defects are, in my term, what I mean by excitations. Okay.
Question then. Is
Okay.
there no global symmetry here, including certainly including non-invertible or non-invertible symmetry? But how about people talk about categorical symmetry?
So here we don't consider any symmetry. Maybe it's kind of there are some kind of gauge symmetry, but there's no global symmetry for either invertible, non-invertible, or and higher form, none of those.
Right, but I think I was confused when Xiaogang say categorical symmetry relates to topological order. Maybe I already.
That's true, yeah, but I think that's maybe another topic.
Okay.
Yeah.
Don't know the.
It's kind of a different way to view system with symmetry. You can see the symmetry, the symmetric subspace can be viewed as some kind of boundary of a higher dimensional topological order. There's like duality, but not the same physical system.
And I suppose here the global symmetry here is mostly the internal global symmetry. Whether space-time global symmetry need to be break or it doesn't really matter. For example, like
it doesn't really matter.
Lorentz group Euclidean rotation, that doesn't matter.
Yeah. Okay. So let's take this three-dimensional topological order as an example. So maybe most of you may be familiar with the anions in two-dimensional topological orders. And when we go to higher dimensional topological orders, the difficulty comes from those extended objects. For example, in three-dimensional topological orders, you will have, in addition to the anions or the particles, you will have these string-like excitations. And when you consider the braiding, you will have to use a particle to braid around a string. This is a non-degenerate braiding. And if you only braid, for example, if braid two particles in three dimension, this thing will always be plus or minus 1, depending on the fermionic nature of the particles. And this is actually follows from a very simple argument by the extra dimension, because this braiding path can deform to a trivial path in 3 or higher spatial dimensions. Okay. So this is a simple braiding process, but you actually wonder, well, how complicated can the strings be? Because you have all those I draw these knots here, and there can also be other special links, knots and links of these string-like excitations. And if you really want to exhaust all the properties of these different knots and links, it will be extremely complicated. And the point of this work is actually we managed to avoid this difficulty and obtain a classification from a different point of view. Okay. So the motivation actually comes from the lesson we learned during the study of two-dimensional symmetry enriched topological phases. And one thing we learned is this Tanakan duality. It says you can reconstruct a group from its category of representations. So this rep G is the braided tensor category of group representations. So for example, if I take the group to be the SU2, then the group representations is just the category formed by all the spins. But we also need the actual structures of these spins. Basically, all the linear algebra structures. For example, this direct sum, you can have different spins in a degenerate state. So this is just the direct sum of different spins. And you have this tensor product of different spins. And a typical example is if you have two spin 1/2s and put them together, you can decompose the total space into the direct sum of spin 0 plus a spin 1. And in addition to that, you have to specify the basics change from this tensor product state to the spin 0 singlet and the spin 1 triplet. And actually the matrix of this basis change is just the CG coefficients. And besides those structures, you also need to specify this, because it's a braiding. You also specify what happens if you exchange two spins. And in this case, they are just bosons. So the exchange is just exchange, no other phase. But if you like, you may also choose some fermionic exchange. And so more about this reconstruction is actually, if you know this RefG or all the linear algebra structures, then you have this Vergecto functor from this category to the underlying vector space that you forget how the group, how the SU2, for example, acts on the reputations. You just take underlying vector space, and you take this. Actually, this basic change is something known as an intertwiner. It's a linear map that preserves the group action, and this Vergecto functor also maps this intertwiner to some linear map and forgets about how it intertwines the group action. And then Tanakan duality says a group is the same as the natural transformations, the invertible natural transformation from G to G itself. Okay, but this is not good enough. Actually, there's a better theorem by Deligne. Well, Deligne's theorem says any symmetric tensor category must be of the form of the representation of some group. So technically, this is something more than the Tanakan duality, because Deligne actually says if you have a category and it is a symmetric tensor category, then you can construct a functor from C to here is actually the super vector space. And then you take the automorphism of this functor, and you'll find, and then you construct these representation category of this group. You'll find this is the same as C. So this, well, there are some technical difference from Deligne's theorem and Tanakan duality. And Deligne's theorem actually tells you, once you know the braiding of the category is braiding of the, or as braiding of the particles are boson or fermion are trivial, then you can always extract a group from this category. So when knowing this, you immediately, together with the fact that in three-dimensional or higher, the particles braid trivially, they have to be boson or fermions. You immediately know in the total orders of 3+1 or higher, there must be a group hidden in the particles. And then there are some natural conjecture about what three-dimensional total orders can be. And the first conjecture maybe can they be just ordinary gauge theory? And the answer is certainly no, because we already know at that time we already know there are many examples beyond gauge theory. But what about this digraph-ridden gauge theory? Is this gauge group plus some false cohomology group, this false cocycle twist. And our answer to this question is yes, if all the particles are bosons, if there's no emergent fermions in the particle spectrum. And what if there are emergent fermions? The answer is, well, a bit complicated, but you can put all those complicated things in a simple sentence that they are all gauged fermionic symmetry protected topological phases.
Okay, many questions, sorry.
Okay, sure.
First, can you remind me what's rep G, comma Z? What's the Z? Maybe I didn't hear.
You mean the last?
The Lin theorem says no rep G, comma z, the Deligne theorem.
Okay, rep G comma z. I'll be explain this in later the details of. So this Z is basically the fermion parity if it's non-trivial.
So it's a Z2 graded somehow.
Yes. So this is if Z is non-trivial, then GZ is a supergroup with Z being the fermion number parity. And if Z acts on some present representations non-trivially, it means that representation is fermion. So this Z provides this Z2 grading on the representation on the particles. But it's also possible that this Z is just the identity element. Then it's the Euro rep G.
Okay. Maybe you will explain even more later.
Okay.
So the second point, you say the symmetry charge of certain group. Do you just mean representation of that group? Or?
Yes.
Okay. And the third question is, when you say Dalgo-Witten theory of some G, do you consider higher group?
No,
like,
no. Just one group, ordinary group.
Oh, then when you gauge fermion SPT, do you also consider more general symmetry?
No. Yeah, also the ordinary group.
I see. Okay, and this will be shown somehow later.
Yeah.
I also have a question.
Okay.
When you say the duality between G and rep G, is that something more than the Fourier transform between like this duality?
Yes.
Is that encoding more information or?
More information. So the Fourier transform basically applies only to the abelian group. And for abelian group is just the character of the representations determines the group. But if you have non-abelian group like this SU2, you have to know some more informations to reconstruct the group. Yeah.
Thank you.
Okay, let me move on. So here is basically the outline or the logic, the line of thinking of how we obtain the results. And as some background, I will introduce basically some simple higher category picture of the topological defects, and then the boundary block duality. So here I'm basically following Professor Wen's definition that the boundary is just anomalous per order, and the bulk theory is anomaly-free, and the anomaly of the boundary actually corresponds to the bulk. Or in other words, this boundary uniquely determines the bulk. Or if you calculate the anomaly of the boundary, you get the bulk theory. And what we really do is first note that the particles with trivial mutual braiding, they determine the hidden gauge group. And then we condense, because these particles, you can condense, if they are all bosons, you can condense all of them. If there are fermions, you can at least condense half of them. Okay, we condense all these particles. And for the case with fermions, you can do some more tricks by condensing the fermion flux loop excitation. After doing that, you will be able to create a boundary. And then we start this boundary. We by this condensation and this gauge group, we know part of the property of the boundary, and we then study what kind of boundary are possible. Basically, we classify the possible boundaries with respect to certain constraint. And then after doing that, we know possible boundaries, and they in turn determine the bulk by this boundary bulk duality. So that's basically the line of thinking. Okay.
Question?
Yeah.
I think one should clarify because anomaly is a very ambiguous word. I think anomalous here really not mean this invertible anomaly, and usually in QFT context, I don't talk this as anomaly. So you are.
Yeah, I agree. So so here is just boundary block duality.
Okay.
If you want to be more specific.
And the hidden gauge group, you mean is there some magnetic dual or some notion like that?
Oh, it's the group reconstructed from the category of the particles by the Tanakan Duality or the Lin theorem I explained earlier.
Okay, what will you give an example of this hidden gauge group? Maybe for some simple example.
Well, I don't know. Well, what kind of example you would expect?
Yeah, I'm not sure what's the message of this point about point line excitation determine a hidden gauge group. What's the emphasis?
So the logic is like this. Because the particles in 3 dimension braid trivially, and then by the Lin theorem, you can all the particles must carry the representations of certain group. That is what I mean is hidden gauge group. So for example,
in other words, you can say that the particle have a fusion and they're braiding trivially, but those fusion between particles can all be regarded as a fusion of a group representation. So that's a cover all the case. So you can always view fusion of particle as a fusion of a group representation. So that's you can extract the group from that.
But you here is actually a gauge group. So the symmetry charge really mean representation.
Well, it turns out to be you can think that as gauge group.
Yeah.
Yeah, and also there's like a small result we have proven in the paper that all the string excitations you can think them as carrying the flux or the conjugate class of this group.
Okay, and the symmetry charge will be representation of the dual gauge group. That's what you want to say.
Why dual group?
Well, because you are referring this sentence from the next slide, so that's why I asked. Because I was asking dual gauge group, and then you flip to the hidden gauge group, or maybe hidden gauge group, and then you go back to the previous slide. So I was asking whether symmetry charge means that representation of this hidden gauge group. Is that
yes?
Okay.
Yes.
Will you give maybe one example later about this, if that's important? Yeah, because I don't know how I should appreciate this.
Okay.
Yeah, maybe later or whatever. Just. Yeah.
But that's hard because if you see an example, maybe you mean I need to give you maybe some theory to really realize 3-dimensional order.
Okay.
Or
I think one example. One example is that you may have a Z2 fusion. A and A fuse into trivial, and this Z2 fusion just give you a Z2 group. That may be the simplest example.
Okay. Yeah,
this mode 2 conservation gave you Z2 group.
Yeah, it would be nice maybe give some Dargo-Witten type of gauge theory example, just discrete twist gauge theory, and it'll be obvious what is the group you are talking about. Maybe
in that case, just the gauge group of Dargo-Witten.
Oh, I see. Then why is it hidden?
Because I start from some maybe general to our order, and I don't know whether there's a gauge group. It's not true. You have a gauge group for two-dimensional to our orders, right? It's not always you can use a gauge theory or even Dargo-Witten gauge theory to describe some two-dimensional to our orders. Okay. And I don't assume that's true from the beginning for the 3-dimensional thing. So that's why I say hidden group.
So somehow you can extract this topological.
Yeah, I can extract this group from the fusion and braiding properties of the particles.
Okay, okay, great. Then the fourth bullet point, the one about condensing enough excitation, but you also have a problem if you condensing too much. Will that be also an issue? There's a compensation between not too much, but
I don't know how can you do.
There's some.
Not too much is inconsistent.
Too much will be inconsistent.
Once you condense enough, and you get you force the system everything to everything confined, and you go to the trivial state, vacuum, then you have nothing else to condense.
Right.
Right.
Yeah, I say that there's some maximum and minimum bound such as limits, and that's a boundary you will consider, which is gap boundary. Is that the only gap boundary?
It's a gap boundary.
Okay. And okay.
Because what we really do is actually a boson condensation.
Okay, thank you.
So the condensing form like a state, all the condensed excitations have zero momentum.
Great, thanks. It would be nice to know the generic constraint you have to define this gap boundary. Maybe you already have the theory somewhere before, but it would be nice to spell out the way you think about this. But thank you.
Mm-hmm. Okay, so
could I ask, is a corollary of this hidden gauge group that all the charges have like integer quantum dimension?
That's right, it's true. Yeah.
Is there some intuition for why that's the case in 3+1D?
I don't know. Maybe that's a direct result of this trivial braiding.
Mm-hmm.
Yeah.
So when it's not integer,
so as long as you have trivial braiding, then the particle cannot have non-integer dimension. I have to have integer dimension.
I don't know whether this may help. You know, there are two kinds of a point-like excitation. One is that when you join two different string excitation, the domain wall can be viewed as a point-like excitation. But those point-like excitation can have a non-integer quantum dimension. But here, what Lan Tian talked about is a point like this excitation is like a domain wall on the trivial string. And yeah, they have all kind of braiding, so maybe there's more constraints. So this kind of point-like excitation somehow always have integer quantum dimension. Yeah, this is indeed quite magical.
Yeah, I don't know how to. Well, it's kind of, you can think that's a corollary of the Lin theorem, but without really introduce all the details about those. Well, maybe even I can explain all the details. I don't know more intuitive physical way to explain why.
Thank you.
Okay, so this simple picture of this higher category. So the so-called one category is just some algebraic structure consists of two levels of things. So the first level are called these objects or zero morphism. And you have the one morphism, which are arrows or relations between the objects. So that's the one category. And in a geometric picture, you can think these objects are some points in your space or manifold. And then the one morphism are the paths from one point to another point. And then the two categories, you just add some more relations beside the 0, 1, and you have two morphisms, which are the arrows or relations or homotopies between the one morphisms. And again, in this geometric picture, you have when you have two paths, you can deform one path to the other. or you can, or in other ways, you can think this a homotopy of the path. That's a two-morphism. And again, you can do that inductively and define n-morphism as the arrows between n-1 morphism. You can do that, climb the ladder higher and higher. That's basically you can do, well, this n-category thing is some kind of this inductive definition, inductive of relations of homotopies. The point I want to make here is this n-map K-morphism, or this number, this order or level of morphism is just actually the dimension of the manifold of the space-time, as this figure already indicates here. And the n-morphism actually can be composed in n ways. So for example, this one morphism, you can consider the compose of the one morphism is just kind of compose the path. So you go here to here and then to there. Then they together give you a total path that's composed of one morphism only one way. Two morphisms, you will have two ways to compose them. The first one here, maybe all you already call the horizontal composition, is you consider you have a two morphism here and two morphism here, and then you can compose them to get a surface or homotopy between the upper path and to the lower path. This one way of composing two morphism. The other way is you can also have some two morphisms like this, another path, third path, and then a two morphism. And you can compose them vertically. That give you two morphism from this upper one to this lower one. So that's two morphism. You have two ways to compose them, and in general, n-morphism, they are like n-dimensional objects, and you compose them in n different ways in the n different directions in the space. Okay, this is not actually the picture we'll be using for the defects. For the topological defects, actually we are taking this dual picture. So the zero morphism, or the object, is actually the topological phase that occupying the whole space-time. And then the one morphism will be the codimension one. So the defect is one dimension lower than the total space-time dimension. So that's one morphism. So the relation here is actually defects on defects increase the level of the morphism. So K morphism are the codimensional K topological defects. So you can have, like, here you have this maybe a phase, two phase here, and you have this two-dimensional example. Then the one-dimensional defect between them, they are the one morphism, and you can even have this zero-dimensional defect between the one-dimensional defect. That's a two morphism. And again, the composition of K morphism here will be translated to the fusion defects. It's like you have two defects and you fuse them together. They together give you a composed defect. Okay. And we list all the levels of structures of this n category. So if you assume this total space-time dimension is n+1, then you count from the phase, that's the codimensional zero, or this spatial dimension is just n. That's the zero level, and the codimension 1 defect, codimension 2 defect, until the n-1 codimension n-1 defect. that is actually the Lan defect that has spatial dimension 1, and then point defects are the n morphism, and also the physical operators. They are n+1 morphism and occupy 0 dimension in space-time. And if we collect all of those, we should have some. We should have a category with 0, 1 till n+1. That's a n+1, n+2 levels of structures, and that's a n+1 category. And surely we should have, besides this, well, basic data, we should have other constraints, other structures of this category, but I will not really elaborate on those properties because they are not very important, well, very essential in understanding this logic of this classification. Okay.
So here I have a question. When you consider this n+1 category, do you concentrate on the category with only one object? You think about the category of many objects. So basically, that's a category of many different topological order.
Yeah, so this is a category of all the n+1 dimensional topological orders, and each object corresponds to a topological order.
Oh, I see. So all the topological order are in this single category.
Yeah.
Okay, thank you.
And I think maybe we have some conjecture that this is just the n+2 vector space.
Okay.
Yeah.
Okay. Yeah. Thank you.
Just to make sure the dimensionality. So when you say codimension, do you mean codimension with respect to the spatial dimensions or space-time? Like earlier slides, you also have this.
The total. So.
Total, or just space.
So for example, when I say here spatial dimension, I mean one lower than the spatial, but time is untouched. So the bulk phase is actually n spatial dimension and n+1 space-time dimension. So this difference is just the same. You don't need to worry about codimension with respect to space or with respect to space-time. Just one lower. That's codimension 1.
When you say n+1 dimensions on the top of the table, you mean what's the?
This is space-time. This space-time.
Okay. But let me just confirm. Sorry, the earlier slide, one slide earlier, when you say codimension, one slide earlier, you say K morphism are codimension K. Does that imply codimension respect to the space or space-time?
Yeah. So I want to say is the same respect to space-time or respect space.
Okay.
Yeah, so you can look at this, for example, this object. Its space is n is 0, so total minus 0, and its space-time is n+1. It's n+1 minus 0, so that's the same.
Okay. All right. Thanks.
So I should say the codimension K is respect both spatial or time. I mean you subtract the same dimension from the total one.
And you'll use both case on the purpose for this comparison of codimension has different purpose. One is for the space, the other for space-time.
Well, I just think there's no need to distinguish them.
Okay.
Yeah.
All right. Thanks.
Okay. Then the question is how we describe the topological orders in some more concrete categories. And again, let me recite this definition of anomaly-free and anomalous. So by anomaly-free, I mean a series topological order which can be realized by some lattice model in the same dimension. And anomalous means it must be a boundary series of lattice model in one higher dimension. Okay, then we want to give a concrete description of some topological order in this TO n+1. So we fix objects in that. Then there are, so I said, my definition of excitations are just the morphism or the defects between the trivial defects. So the trivial defects are just algebraically the identity morphisms at different level. So by definition, the zeros is just C itself, and the first one is the identity morphism from C to C, and then the case morphism adjusts the identity morphism from the k-1 to k-1. Then we can just take this this home category, which includes all the codimension k excitations, including the defects, higher dimensional defects on them, and that's the codimensional k excitations. Okay. Then we want to see the category C is actually described by the properties of excitation in it. It is just this home category, and it will be a n+1 category with only one zero morphism, and this is by definition a monoidal n category. And I use a different font for this special category. And this monoidal means that you can fuse the object. So actually the codimensional one defects, you can fuse them, but there's only one direction you can fuse them. That's the meaning of this monoidal or this monoid, this multiplication. But in really physical applications, we actually require some nice properties like the semi-simple or condition complete. So actually, we require this not only a monoidal in category, but also a fusion in category. But I will not really explain the details. Maybe in Theo's talk he'll explain more. Okay.
Excuse me. So here, this category of topological order, actually the object can be potentially anomalous topological order, right?
Yes, that's right. Yeah.
Okay. Yeah.
So also, so I forgot to say the key message of this slide. So, so the fusion in category is actually the description of a potentially anomalous topological order. And then we also want a description of anomaly-free topological order. And the idea is the braiding degeneracy, because in topological series, there's no other way to probe topological excitation besides braiding. So this necessary condition for anomaly-free is all the topological excitations must be detectable via braidings. And then we know this codimensional, the excitations of codimension greater than 2, only those can braid. The codimension 1 excitations or defects, they cannot braid because there's no room for the braiding path. So if we want to consider the braiding, we have to take this n+1 category by fixing the zero morphism, this object C, also topological C, and also fixing the trivial codimension 1 defect, or this one morphism, and then take all the codimension k greater or equal than 2 excitations, and the by definition forms a braided monoidal n-1 category. Then again, we add these physical requirements of fusion, and then add these braided non-degeneracy requirements. So the conclusion is to describe anomaly-free topological order, we should use this non-degenerate braided fusion n-1 category in n+1 dimension.
Excuse me.
And what about the codimension 1 defects? They cannot braid, but they can somehow half braid. So the conclusion is actually they should be determined by all the codimension 2 or higher excitations via the so-called condensing completion. That's the suggestion by Galdo and Johnson-Phil. And question?
Yes, naive question first. Sorry. When you say braiding is only physical probe on the top in topological series, a necessary condition for anomaly-free is the one in the quote, right? The braiding non-degeneracy.
Yes.
And just make sure.
So that simply means if you cannot detect something, you should not include that in your physical theory.
It's necessary, but not sufficient.
And
also, okay.
I don't know whether it's sufficient, but in 2+1 is sufficient. In higher dimension, I'm not quite sure. Probably still has a proof that it's also sufficient.
Let me make sure. Just make sure mapping my logic is slow. So suppose there are some excitation may not be detected by braiding in its own dimension. Is it possible that theory can be anomalous? Or it cannot even be a serial, I don't know, just maybe some.
That depends. If that is consistent, it should be just an anomalous theory. You should use some higher dimensional things to detect the things that cannot be detected in its own dimension.
Okay. Yeah. This point I get. Okay, thanks. That's right.
Yeah, here I have a question about the the codimension 1 defect do exist. It's allowed, And
it's allowed.
Yeah, but physically we think, oh, they are descended from condensation of a higher dimensional object. That's a kind of more physical argument. And you just mentioned that whether mathematically, whether there is some other point of view, actually this dimension 1 excitation is allowed because they can be detected via some other things. You mentioned something half braiding, I try to say whether not using this physical condensation, whether there's another way to think about this.
I think at the end of this part, I will give you more rigorous definition in terms of the trivial center, and I think.
I see. Okay.
I think this maybe a corollary in Steele's paper that when that condition is whole, this statement is true.
Okay. Thank you.
Yeah. So next, let's go to this boundary block duality. So the idea is actually simple because when you have a boundary theory, it should physically it should also involve some neighborhood near the boundary, but since we assume our theory is topological, then this small neighborhood, maybe this small neighborhood here, by the topological requirement, there's no scale dependence. It's already the same as the whole bulk in the larger distance. So this is basically the physical idea behind the boundary bulk duality. Why boundary theory should determine the topological bulk theory. And mathematically, we have this formulation that a boundary mathematically described by the fusion in category, it should uniquely determine the bulk, which is a non-degenerate braided fusion in category. So that's the dream field center in higher dimension. So for n equals to 1, that's the usual dream field center, which if you input is fusion 1 category, it gives you or constructs a fusion a non-degenerate or modular tensor category 1 category, yeah. And the constructions is well known. For example, the tutorial we wrote TQFT and level model, that's for the n equals to 1 or the 2+1 case from the 1-dimensional boundary to the 2+1 and bulk. And this Waterloo model is a special case for n equals to 2. You can view that as some, it requires the input fusion 2 category to be some special case, maybe only has a point like excitations, no strings. Then your Waterloo model can construct a 3-dimensional bulk. And so when we have this dream field center, higher dream field center, we can restate this anomaly-free condition in a more rigorous form. That if you given a fusion n category, then we compute its dream field center. If this dream field center is trivial, that means this boundary actually don't need a non-trivial bulk. This bulk is a trivial bulk. So in turns, you know this fusion n category is actually anomaly-free. So this just this Z1 and this dream field center is the way to compute the anomaly.
Naive question. On the top line, say a boundary fusion n category uniquely determine the bulk of non-degenerate braided fusion n category. But I suppose the boundary theory can also have some braiding. So why is the boundary theory you start with?
Yeah, when this n is bigger than 1, then there are braiding in the boundary. Sure.
Okay. So can you modify the statement if you also include braiding on the boundary?
But those braiding are for the one morphism or higher morphism. The objects don't have a braiding.
Oh, okay.
So basically, if you want some concrete or definition, is try to give the braiding to the object in the fusion n category, and it promotes that from a fusion to a braided fusion. Because braided fusion means there are braiding for the objects. So as long as this n equal then n is bigger than 1, then the higher morphisms have braiding is an automatic thing.
Okay.
Yeah, I have a question. You mentioned about this monodal fusion n category. Oh, sorry, monodal n category and the fusion n category. So there's some fine distinction. And here there is an issue of computing the dream field center of bulk. I wonder whether a fusion category already have all the data which allow you to compute the dream field center, or whether maybe monodal n category don't have enough data. There's some subtlety here.
No, I think as long as you have monoidal, you should have this dream field center.
I see. So monodal already
monoidal is enough
information for computing dream field center.
Yeah, but if you add those other structures, the fusion like linear or direct sum, it's a concern that whether they will be preserved on the image. So the output, if you compute the dream field center of a monoidal n category, then the output is a braided monoidal n category.
Okay.
The non-degeneracy and fusion conditions, you have to deal with them case by case, I think.
I see. So the point is that for the fusion n category, it indeed contained enough data to compute the dream field center. But however, whether those nice property would carry over to dream field center, that needs more work.
Yeah, that's right.
I see. So is this something still kind of work on by mathematicians? So computing this dream field center to see whether all the nice property carries through or not. Is this open? I wonder whether it's still open question,
well,
open issue.
maybe I don't know if I think that still should have solved this in terms of his definition, but maybe he didn't solve this. If I also add unitary fusion category, maybe.
I see.
Yeah.
Well, you get the unitary non-degenerate braided fusion category. Okay.
Yeah, I implicitly assume everything is unitary.
Okay.
I didn't write everything, write unitary everywhere.
Okay, thank you.
Question about the non-degeneracy. So can we relate the non-degeneracy in 3+1 with some form of S matrix like in 2+1?
It's not that easy, you know.
I see.
Yeah, it's not that easy. So in 3+1, there will be a bit more data you have to check.
Can you be mapping classical with some manifolds?
I don't think so. Maybe.
So I guess the 3-string braiding is related to this SL3Z, right? So is that notion of S matrix sufficient to?
You mean the three loop braiding?
Yeah.
Well, the only thing I can see is that the non-degenerate braided fusion, two categories, non-degeneracy here implies the non-degeneracy of every 3-loop braiding.
Mm-hmm.
But the other direction, I'm not sure.
Okay, thanks.
I have a question. So if I look at the first line, I think I understand what happened in 2+1D if you take a fusion category and then you can take a center to get the bulk. But I'm kind of confused if I combine it with the second statement. Does it mean that only when the bulk is trivial, the boundary is considered anomaly-free? Is that the definition of anomaly?
Yes.
Meaning that meaning that in most cases we're dealing with so-called anomalous boundary, anomalous theory, when we do any form of Levin-Wen construction. Maybe it's definition, but I want to understand.
Could you repeat?
So I'm looking at the anomaly-free condition, and then I know, in most of the Levin-Wen construction, we start with a fusion category such that its center is not one, right? And that would be considered anomalous in some sense.
Yes, yeah. In the fusion 1 category are all anomalous.
I see. So okay.
But the fusion 2 is, well, it's hard to say. It's not always anomalous.
And by anomalous, it kind of means some uninvertible bulk. Would you think of the two as?
Well, yes. So all this framework cannot distinguish the invertible phase, so it's up to invertible things.
I see.
So this one actually means potentially just an invertible topological phase in the bulk.
I see.
It also has trivial category. So, well, in this categorical framework, you cannot really distinguish invertible things.
I see. Thank you.
Okay.
Related to the question is that for this non-degenerate braided fusion N category, can we say that this non-degenerate is defined as their Greenfield center is trivial? You can take additional Greenfield center.
Yeah. So that's the non-degenerate here. So it actually means the E2 center or selected center. Now in N equals to 1, that's the Milger center.
Okay.
Yeah.
Okay.
So basically, E2 center is trivial, means non-degenerate.
Okay, okay. So it's an E2 center. Then there's E3 center. You have the E3 center in the higher category. Or maybe only E2 centers involved here. Okay.
Well, yeah, so it's braided, so you can only up to compute up to E2 center.
Okay, yeah, thank you.
Symmetry can compute E3 center and higher.
Okay.
Yeah, and maybe just a comment. If you compute this center twice, is that compute the bulk of a bulk, because bulk is already anomaly-free, so this D applied twice gives you automatically trivial. So this also two orders actually have a co-chain structure. That's just comment. Okay. Okay, so let's basically finish the boundary block duality part.
Oh, sorry, co-chain structure. You want to comment is respect to what?
So I mean,
respect to co-boundary or cocycle, what concept you are trying to?
Because if you take this Z1 twice, it's always trivial because Z1 is already a bulk.
I see.
So it's like this is zero in a co-chain complex. So you can think this Z1 is the derivative. If you apply that twice to any lower order, you get trivial.
Okay. Thanks.
Okay, let's move on to this trivial braiding. And the reason is actually simple, because if you braid some excitations whose dimension is low enough compared to the space-time dimension, you can always deform the braiding path to trivial. And in particular, in 3+1, this means particle and particle braids are trivial. And if you have four spatial dimension, and the particle and also particle string braiding will be symmetric. And if that's 5+1 or higher, then also string braidings become symmetric. And if you do that more generally, you assume this space-time dimension is n+1. And then you take a p-dimensional excitation and a q-dimensional excitation. You want to compare the worksheet of this of the two excitations, that's p+1 plus q+1. Then you want another dimension for you to do the braiding. So you compare n+1 with p plus q plus 3. And if this p plus q is smaller than the n-2, that means you can always leave any crossing of the two excitations, the path of the two excitations to trivial. Then the braiding is symmetric. And if this two quantity happens to be the same, then this braiding cannot be lived. There's no extra room to lift any braiding or crossing between their braiding paths. And this, in this case, the braiding should be, in some sense, non-degenerate. So the p-dimensional excitations can detect the n-2 p excitations by braiding. And if p plus q is greater than n-2, well, this you can always extract some meaningful braiding information by decompose. By first do dimension reduction to some dimension reduced excitations, and also you decompose the braiding path to some segments, different segments, and compose those together. But this is basically some manipulation that you can do in the higher category. The key idea is actually this braiding non-degeneracy actually is like kind of a pairing between the excitations with complementary dimension. And you immediately see well, quite large difference between these odd or even spatial dimension. If the spatial dimension is odd, then the low and high dimension no excitations, they are always paired. But if this n is even, then in the middle level is n half n minus 1. Those excitations pair with themselves. There's a case like, for example, in 2+1, anions pair with anions. Anions have non-degenerate braidings with anions. But in 3+1, the particle pair with strings. So they are the pairing is dimensionally separated. Okay.
So here, like, I have a question about the dimension reduction. For example, do you mean when you have a string excitation, you can view a small loop as a particle? Is that what you mean by dimension?
Yeah, so that
okay.
Maybe an example is this 3 loop. You can well consider this braiding of 3 loops, and that basically maybe let me use a different color. So if you want to braid that string and do some kind of this braiding, and the first half you can well shrink this loop to just a point particle on the base string, and that's a braiding between this loop and the particle. And the second half, you should shrink this string to a point and consider that as a braiding between this loop and that particle. So the whole braiding can be decomposed to 2 steps. Each step is a braiding between a loop and a particle.
I see. Okay.
Basically, everything like in this case can be done in a similar ways.
Okay.
Okay. Yeah. So now let's focus on this 3+1 case, and just kind of repeat what I've explained before. So in 3+1 or higher, the particles. So the first point, the particles have trivial double braidings, so they are boson or fermions. Then by the Lin theorem, they should form a symmetric. They form a symmetric fusion category, and by the Lin theorem, they must be the category of some group, some supergroup, and this rep GZ, this GZ is unique determined by the up to isomorphism by the fusion and the braiding of these particles. And well, I explain here this what Z is. Z is element in G who squares to trivial, squares to the identity, and it is central. It commutes with all the group elements in G. And so one case is this Z is actually the identity element, satisfies this condition. And in this case, this ref GC reduced to the Euro group representation category. And if Z is non-trivial, then it physically is the fermion parity, and the representations where the Z acts non-trivially are fermions. So depends on the action of Z, you can have a grading of the representations. So non-trivial grading means fermions, trivial grading means bosons. Then the okay, so yeah, so in 3+1, there are only point like and string-like excitations. Well, the membranes are actually some condensation descendant, and we don't consider them here. We only focus on the point and string-like excitations. And the point or particles, point excitations, they are actually fully determined by some group or supergroup. And the braiding non-degeneracy means all the strings must be detectable using this point, using these particles. So it's naturally expect to classify all the orders, you only need this GZ, this group data plus some maybe extra data. But it's hard to extract all the, as I showed you at the beginning, well, the strings can be extremely complicated with various nodes and links. So those difficulty also is here for this braiding monoidal 2 categories. And what we really do is using the condensation idea. Okay, before discussing that, here's a conjecture, because I will just analyze something about general dimensions. So maybe for all the odd spatial dimension node orders, because the low dimensional excitations, they have trivial braiding. So you may be able to have some generalized theorem like the links, and maybe they are always the higher representations of a higher group or supergroup. Then the braiding non-degeneracy between the pairing of, it gives you the pairing of low dimensional and higher dimensional excitations. So the half of the excitations that has high dimension, they should be maybe also determined by this group plus some maybe just extra data. So the conjecture basically means maybe the all dimensional orders are all kind of gauge theory of group, gauge theory, yeah. Okay. Now let me explain more about this condensation idea. So put it simply, by condensation, we just want to add some extra interactions to make a certain subset of excitations to condense. And the point I want to make is whether this subset of excitations can be condensed or not only depends on the properties of itself. If you have extra excitations, or maybe your dimension is very high and you have maybe a higher dimensional excitation, other excitations besides this fixed subset A, they don't affect the ability to condense or not of this subset. And why is that? Because what the condensate we want is actually some C of these condensing excitations, and all the excitations in this subset should be able to fluctuate freely. So let me denote this condensate by this psi A, and this W some operator that can create excitation in A. So for example, this open Wilson loop operators that can create two particles on these two ends, and maybe or surface operators that can create a loop around this boundary. So this W maybe means all kinds of those operators that can create or hop excitations in the given subset A. Then the condition that I want the excitations to be fluctuate freely means if I apply this W operator, any kind of W, to this condensate state, I should get the same state. And there should be even no phase factor, because phase factor in general will be destructive and destroy this condensate. Okay. Then we get a corollary that this condensation, if condensation is possible, then that also means all the possible W operators should have this equals to 1 as the most favorable state for this psi A. And then this W should have commute. This should commute within this low energy subspace. And to really force this condensation, we only need, so the only thing we need to do is to add this interaction of this form. Energy, this factor is that goes to minus infinity, and this projection is the interaction that forces this +1 eigenvalue of all those Hoping operation operators. So add this thing to the original system, we will force a condensation of this excitations in A. So necessarily this W should, well, they all commute. That means, well, because in particular, the W includes the operators that describe the various braidings of condensed excitations. Because, for example, if you have like maybe a Wilson loop, another Wilson loop, you can, so this is W1, it's W2, and this order of applying W operators to your condensate. And just one way, and you can do that another way by applying this W2 first, W1 first, W2 second, and any ordering of this applying W operators should give you the same condensate state. So that means this. So the difference of these two is just the braiding of this if I have particles here. It's kind of a braiding process. So the condensation is possible. Is the necessary condition is the mutual statistics, the mutual braiding of the condensed excitations must all be trivial. Okay. And well, to be honest, the general theory of, well, how you can condense higher dimensional excitations, the extended excitations is not very clear, but when you can condense particles is well developed. If you only want to condense pointed excitations, then it is known this A must have a algebra structure, or there are, well, requirements, conditions for this algebra. It must be a connected, commutative, separable algebra, or some Frobenius algebra. There are different criteria for this, and special condition is a corollary of this is that all the excitations in A must be bosons. Okay. So let's put this in this 2+1 dimensional case. Consider two-dimensional orders C, and we can choose A in C to condense that, and the result will be new. So in this area, in the D area, we add the interactions described earlier. After doing that, we should obtain a new phase, and together we also got a gapped defect between C and D. And this A condensate is just a new vacuum in this D's new state D. And all the excitations in D and on this defect M should be something that is, or they can be surrounded by this A. So they are mathematically the permutations or the modules over this algebra D. And after we do this condensation, then depending on whether the excitation that is not condensed, so excitation not condensed, depending on whether they have mutual statistics with the condensate or not, they can be divided into two classes. If they have trivial mutual statistics, because this A is the vacuum here, so excitations in D must be able to go around. So it must have trivial mutual statistics with condensate for this total phase to be non-destructive. So only in this case they are deconfined and they can be excitations in the new phase. And if the other excitations have non-trivial mutual statistics with A, they have to be confined and they are actually stuck on this boundary. They can only move on this boundary and they cannot go into the new phase D. And in mathematical term, this new phase is just local or selected modules, A modules in C, and this gapped boundary is all the A modules in C, because they include those local modules. The excitability can go back onto the boundary, so they are included in the distribution of N. All these things are actually very concrete construction in 2+1 case. Okay, but
Sorry.
then okay.
Naive physical question. Maybe previous slide. When you say the interface excitations that can move into the A have trivial mutual statistics, and you call deconfine.
Yeah.
I wonder, in the very beginning, you say if there are some excitations, you know, if these are anomaly-free, you call topological order, then every excitation should be detectable by some braiding. But I just want to make sure how these two concepts are put together. Do you understand what I try to say? So one is about a non-free topological order. Every excitations should be detectable by braiding.
Mm-hmm.
The other one is now you say that the interface excitation can move into the A only when you have a trivial mutual statistics with A. With A means with A's condensed excitation.
A is a condensed thing. Yeah. So anything in A is actually the vacuum in this new phase D.
Okay. Yeah. All right. No problem.
So because it's A, you can think well, you can freely create something in A and then annihilate that. So the excitation that can survive in this new phase must be able to braid with things in A in arbitrary ways.
Yeah, it can still be have a non-trivial with excitation inside the D region, but just not the.
So with themselves, they have to have non-trivial braiding. So the deconfined excitations have non-trivial braiding with deconfined excitations. So I think there's no contradiction.
Yeah, no problem.
With braiding non-degeneracy. Okay. So the story for the two-dimensional case similar. If there's a subset A that is large enough, or mathematically is known as the Lagrangian algebra, whose dimension is large enough, then the new phase D is trivial. In that case, this M is actually not interface, is actually a boundary of C because D is trivial. Then we can compute C as the dream field center of M. But the bad thing for 2+1D is not every C, not every 2+1 square order contains a Lagrange algebra. Or in other words, not every C contains a large enough subset of excitations that can be condensed consistently. However, for 3+1 case, since this braiding non-degeneracy, actually the dimension separately of particles and strings and particles have trivial braiding. So you always have half of the excitations, actually the particle are the half. The particles have trivial braiding, they are bosons, you can condense all the particles. In this case, they are actually large enough. So in some sense, they are Lagrangian in the 3+1 dimensional order, and condense them, you can be able to create a boundary. So that's why the idea of condensation works in 3+1, but not in 2+1.
So in 2+1 dimension, if you have a topological order which contains Lagrangian algebra, whether they are classified by the fusion category in a one-to-one sense.
So that's exactly the class of string line model.
Yeah.
Model, yeah.
But it may not be. But even in that case, it may not be one-to-one. Yeah, right.
Not one-to-one. Yeah, the boundary can be many
many
boundaries to one block. Yeah.
I see. I see. Okay. Yeah.
Okay, then comes the actual result. We have to, because formulas cannot condense, so we have to divide the case into two subclasses. The first class is this all boson toroidals. If all the point-like excitations, all the particles are bosons, then they form this rep-G of some, not super group, just Euro group. Then we can condense all the bosons. After condensing all the bosons in the new phase, there is no particles anymore. So then by the braiding non-degeneracy, there should also be no strings. That means everything, all the boson, all the particles and all the strings are confined. The resulting phase is trivial. So by condensing all the particles, we already got a boundary. So the next problem is just to study this boundary. And it's actually just a direct application of Tanakan duality. So actually, technical detail is actually we study this half braiding between these loop excitations on the boundary and a particle inside the topological order. And we find this every closed loop gives you natural transformation of this group representation category. And so actually every closed loop corresponds to a group element in the same group G, which is we extract using Tanakan duality, using the Lens theorem. So that's the constraint we obtained from the condensation picture. Every all boson topological order have a canonical boundary. This boundary, because particles are condensed, this boundary has no point-like excitation. It has only string excitation. And the fusion of those strings on this boundary are given by a group G. So then the question becomes quite simple. All the possible fusion two categories with only with object fusion given by a group G and no non-trivial two morphisms. All those possible fusion two categories with satisfying this constraint are only those classified as this extra four cocycle. And they are all these G-graded two-vector spaces. And interestingly, this data, this G omega 4 data, is the same as the bosonic SPD phase. Okay, and if we want to get the bulk theory, we just need to apply this trivial center to this graded G-graded two-vector space, and that's exactly the Debye-Witten gauge theory. So that's just finished the bosonic part, the all boson part. Sorry. And for the Taylor orders with emergent fermion, the things is a bit complicated, because now there are the particles, half of the particles are boson and half of the particles are fermion. We can only condense the bosonic part. And after doing that, the new phase is a topological order whose particles has two flavors, just a trivial boson and a non-trivial fermion, or this supervector space. And we actually argued that this resulting topological order is unique, but maybe it's actually not, because mathematicians actually found another solution. It's kind of weird. But anyway, let's assume this is true for the moment. This C4 Z2F C4 Z2F is this twisted Z2 gauge theory, whose charge is a fermion. Then we can study it, and so also maybe you can also construct that using a twisted string net model in 3+1D. And its property is known well. We know this. It has only one types of string excitations. It's just fermion loop, fermion flux loop, fermion parity flux loop. And it has this loop excitation has trivial mutual statistics, and it should be able to be condensed. After that, this special topological order has a boundary. This boundary has only pointed excitations and no string excitations, or up to the condensing descendant. So basically, this CZ24 is the trivial center of this supervector space. Well, the other solution of this 3+1 topological order, whose particle is only boson fermion, may be anomalous, although it may have a, although its trivial center is trivial in the sense that, but this trivial may be a non-invertible phase, a invertible phase rather than a totally trivial phase. So that's basically the discrepancy, or the subtlety here. Okay. So as return to this question of this range of order, we want to classify. So actually we did two steps of condensation. The first step is condense all the bosons. That's half of the particles. And the second step is condense the fermion parity flux loop. And actually we want the just a boundary of the original order. So we can just view this sandwich, this domain wall and the boundary, view them together as a total boundary of the original phase. And then we can study the property of that special boundary. And I will just show you this result. We find this, so I just I kindly partially describe this A3B. It has so on the particle level, there are only trivial and the fermion. The strings are kind of strings of fusion. The fusion strings are still group-like. With the closed strings form this bosonic quotient group GB. It is the GF quotient by this Z2F. That's the closed string. Besides that, when you consider the open strings, there are the Majorana chains form another Z2 group. So this basically is the fusion structure of the strings, and depending on whether this GB and Z2 are direct products or non-trivial extension, we can further divide the boundaries, the topological orders into two subclasses. So this string fusion, GB and Z2M, and particle are boson fermion. And actually, there should be a lot more details because this case is very complicated. There are actual classification data, some cocycles or obstruction conditions. But after examining all of those, we find that all these conditions, all these extra data and conditions are corresponding to the fermionic SPDs in a or maybe just like one-to-one correspondence. So so we can conclude this classification of EFKs simply as they are all gauged fermionic SPD phases with this symmetry group GF. Okay. Okay, so that's basically I want to say. And so the summary of the.
Just make sure. You say the GF symmetry SPD. Let me just make sure the fermion parity is in the normal.
It's normal. Yes.
What do you want to gauge? Not necessary quotient can be gauged, right? Or is the product group GF is a product group between Z2F and some bosonic symmetry?
Excuse me?
I said you want to get a fermionic topological order by gauging SPD. But I say the GF symmetry has a Z2F as normal subgroup and some maybe bosonic GB symmetry.
Yeah, bosonic GB.
You want to gauge GB, but is it product group
GF? You gauge everything. You also gauge fermion parity.
But you want to get a fermionic topological order, which has fermion parity.
But it is a bosonic order with emergent fermion.
Okay, so how about fermionic topological?
Fermionic order. The fermionic order should have like so transparent fermion. That's maybe the definition. So you have transparent fermions. Those fermions braid with strings trivially. That's the definition of fermionic order. So I think it's well included in this classification because you can, if you have a fermionic order, you can gauge fermion parity to get a bosonic order, right?
Sure. But how about
so if you just ungauge the fermion parity, or in other words, you start from a fermionic SPT and gauge only GB.
Okay, but GB may not be normal subgroup of GF.
Well, that's maybe the technical problem.
Okay, but there's a scheme you feel confident.
Yeah, probably we can by engaging the fermion parity to obtain at least part of the fermionic orders.
Okay, thank you.
Okay.
Maybe I can ask afterward. Thank
I
you.
think what Lankan means, it can partially gauge a symmetry group of fermionic SPD states. And there's many choice. If you gauge all the symmetry group, you get a bosonic topological order. If you partially gauge some symmetry group, you may also get a fermionic topological order. But I don't know whether this should be a classification, means all the topological order and the bosonic fermionic topological in 3+1D can be obtained by partially gauging the fermionic SPT states or bosonic SPT states. That's it.
Yeah, that's true. Mention maybe sometimes you cannot gauge these quotient group GB totally, so it may be a problem. Okay, so it's a summary, basically a summary of the logic, and maybe I want to discuss about some recent progress, because it's actually a very old, maybe 3 years before we did this work, and after that, there are some developments on the higher category mathematics. So Douglas and Reuter gave a rigorous definition of fusion 2 categories, and Johnson, Fried, and Galdo gave this definition, this notion of condensing completion. And we can discuss this fusion 2 category, fusion category in more concrete ground. And in particular, I think this what Seal is going to talk next week. He in this paper proposed a more rigorous mathematical definition of topological order in arbitrary dimension and the fusion category, the trivial center of them, like non-degeneracy of them. And he claimed he was able to prove of classification. And here's some work in progress, as we also want to include higher symmetry in this higher topological order framework. Okay, that's all. Can go on for questions.
Thank you very much. Thank you, Tian, for the wonderful lecture. Question from the audience. You can raise your hand, so you can go ahead. You can no priority. I do have maybe 2 questions. We'll see what the others answer. The first one is, how about anomalous? Sorry, let me just make sure. How about the topological order with invertible symmetries anomaly, not non-invertible? Do you have also
invertible symmetry anomaly?
Just maybe 3+1D with some global symmetry with a total anomaly of global symmetry, not on the boundary of some 4+1D topological order. Is that something you already have maybe a enumeration or classification? Enumeration even is okay. Or there are some along your work.
What do you mean by invertible symmetry anomaly?
What? Just invertible anomaly of some
invertible anomaly.
Anomaly of some zero symmetry, ordinary symmetry. Not even higher symmetry. Because what you summarize here maybe is either topological order on its own dimension or topological order on the boundary of one high dimensional topological order. But I'm asking, how about topological order on the boundary of SPT with some internal symmetry, G. And for the if not, it's fine. I just ask anyway.
But I think maybe that's kind of what we done in this
okay.
In this paper, I think.
All right. Maybe I'll ask later. And a second question is, go back to the beginning. You say you don't include global symmetry to topological order, but can we now clarify the meaning of categorical symmetry in this context? What will that be in the classification of topological order in your? Do you also means that you classify categorical symmetry or something like that?
Well, not exactly, because categorical symmetry correspond to some order in one higher dimension. If you give me an arbitrary order that may not be a categorical symmetry, it must satisfy some additional constraints.
Okay, you mean topological order more general. Topological in one categorical.
Yes.
Okay. Can you sharpen this notion if it's possible? Anyway, I just ask because everyone's here. So.
Yeah. So for example, one thing, actually, when we try to compute the categorical symmetry, actually we did the same thing as taking this trivial center. So so for example, if you have let's take an example of maybe one-dimensional system, and it has a symmetry, ordinary symmetry G. Then the excitations on this one-dimensional system must carry the group permutations of this group, right? So just a one-dimensional physical system with group G.
Okay.
Yeah. So for this system, we define or we see this categorical symmetry is just the two-dimensional tuple order who is the trivial center of rep G.
Okay, so category is this object Z1 rapture. Oh.
Yeah, so this tuple order is a categorical symmetry of the ordinary symmetry G.
How would you label categorical symmetry in this case? How you label G is a ordinary symmetry? Sorry. G
yeah, this is the label. Yeah, this is exactly the label. This rep G, this trivial center rep G.
So which is the label of categorical symmetry? This whole things?
Yeah. This whole thing. Yeah, this whole thing.
Okay.
So more generally, so you should have like some kind of fusion category, fusion N category. That is the excitations of a certain system with some kind of symmetry, but this fusion category is not required to be braiding non-degenerate or something, because you can, in addition to use braiding to detect things, you can also use use the action wheel symmetry to detect things. Yeah, so and then this the center of this fusion category is a categorical symmetry of the corresponding ordinary symmetry. That's basically the definition.
Okay. All right, great. Okay. There are some...
And we can use something in this categorical symmetry, some defects, some invertible domain walls in this Z1A to classify, like, for example, the SPT or other things. That's why this notion is useful.
Okay, thank you. Then my question ends. How about Theo, whatever, I'm not sure to pronounce correctly. Theo, please go ahead. Thank you.
Oh, first I thought this was an excellent talk, and Tian sort of gives me some credit for things that were really just like ideas of his that I maybe filled some sort of small details in. But
okay.
I wanted to actually say something about Juven's question earlier about this sort of question about invertible anomalies versus non-invertible anomalies, and you can see it on this slide, so it's very convenient. So something that I guess was from Kong and Wen's 14 paper that Tian mentioned is this chain complex that he writes up, where the sort of yeah, or maybe I'm not sure which paper it is, but the sort of center of the center is trivial. So what one thing to kind of a good way to organize this thing is that what they explained was that you should think in terms of like a cochain complex. This is what Tian sort of mentioned already, where the n cochains are something like fusion n categories. And then and the differential is the center, and then well, that gives you a braided fusion n category, which is the same data as a fusion n+1 category.
Yes.
And so implicit in this is this sort of, you can actually see both types of anomaly through this complex. So that if you're a cycle in this complex, that's when you're somehow a non-degenerate fusion category. And so the cycles are the ones who, if they have, who only have invertible anomaly. So the sort of way Tian was talking about it, then the anomaly of his theory was like the center of the theory. So those are the cycles, were the non-anomalous ones. But there's, of course, when you have a complex, there's a more refined thing, which is the boundaries. And so you might say that only the boundaries are non-anomalous. And the difference is that the sort of cohomology of this complex, the cycles modulo boundaries, is like the space of invertible anomalies.
Yeah.
And so it's really both encoded in the way that Tian was presenting.
Great, thank you very much. Nice, thank you. Rajas, Krishna.
Hello, thank you for the very nice talk. I have a question about the group that is used for the classification. So in 2+1D discrete gauge theories, we can have like different groups giving the same theory, right? But
right.
In 3+1D, because the group determines the whole rep G, can we have different groups giving the same theory?
Different groups maybe not possible, but maybe the same group with different cocycles, maybe they can still give you the same theory.
I see.
And besides, you can have something maybe higher form gauge theory that is not based on groups.
Yeah. So
you use the strings and as your input data to build a three-dimensional lattice model that can give you a theory that is equivalent to maybe a derivation gauge theory based on a group. So the duality is different from that in 2+1.
Right. So all the 3+1 TQFT is defined using higher groups. All of that should be somehow secretly dual to this description, right?
Yeah.
I see. Okay. Thank you.
Great. If Roger is done, next will be Hank. Hank Chen, please.
Yep. Hello. Thank you for the very interesting talk. So I guess just a clarifying question. So for example, if I want to classify crystalline SPD phases in a 3+1D, then the sort of like the space the space group will be part of the bosonic group, right? So
right. Well, yes. So in this classification, actually, I assumed there are finite numbers of excitation types. So all the groups are actually finite, not including the space-time symmetry translation or continuous like U1 or SU2. So only finite group.
Right.
So I should say, well, it's gauged the SPD of finite internal symmetry.
I see. Okay.
Yeah.
So for example, like if we have translational symmetry, then we can just think about the theory on a torus, for example. Or maybe if we have like more refined like point group symmetry, then it will be on an orbifold or something like that. So in that sense, you're not thinking about the crystalline equivalence principle, where you sort of treat the space group as acting on site.
Well, if you talk about that, I think that at the same time you also reduce the dimension, right? like for example, if you consider a mirror symmetry,
Yeah, right, yeah.
It's on-site symmetry on a mirror plane, which is one dimension lower.
Mm-hmm.
Yeah, so I think maybe well, so anyway, so this about the classification of orders, not about general SPDs. So I should modify here. The result is for orders are gauged SPDs with symmetry being finite and internal symmetry.
Mm-hmm. Mm-hmm.
Yeah.
I see.
So
okay.
also that's on acting on 3-dimensional system, not on some reduced plane or line.
Mm-hmm. Mm-hmm. Okay, thank you.
Thanks, Hank. Next will be Nanette.
I had a question about gap boundaries of 3+1D phases. Like from a mathematical point of view, are these rigorously, has this been rigorously like classified?
I don't think so.
Because I guess from a physical point of view, we sort of believe they're one-to-one with like G-symmetric phase, right?
Well, maybe also not, because actually what we did is just find one boundary, one particular special boundary, but not all of the boundaries.
Uh-huh.
So we already see that this boundary is special because we condensed all the particles we can condense. So if you want to find some other boundaries, the thing you want to do is to condense some strings. So that will be, you need to study the algebra of strings, which is, I believe there's no good theory till now. No well-developed theory. So it's still open question.
Uh-huh. I see.
A related issue is that I think in Walker Wang's model, they basically try to condense all the strings and have only particle. But this particle boundary is more complicated, and they do not have one-to-one correspondence with the bulk topology order. But if you condense all the particle have a string-only boundary, and then the relation between boundary and the bulk topology order are much simpler. So that's I think that's a point.
Mm-hmm. But I guess there are also like mixed type
yeah, there must be, but anyway, you have to include some string in your condensation to give you other boundary beside what we have classified here.
Mm-hmm.
And that would be a higher condensable algebra.
Uh-huh.
Yeah.
Because from a physical point of view, I thought they were just one-to-one with since here you're sort of your bulk is like a G gauge theory. I thought the boundary would just correspond to will map to like G symmetric phases.
Yeah, that's just one possible boundary.
Oh, like including like the symmetry breaking ones and the SPTs as well. So.
Yes, yeah.
Yeah, from this point of view, that I think this classification is like consider only symmetry breaking boundary. The symmetry breaking boundary, this is domain wall fusion classified bulk. So if you translate into this language, it's we consider only symmetry breaking boundary.
Yes.
Mm-hmm. Mm-hmm. So there should be something like SPT as well.
You mean the boundary is the SPT?
Right, like I put an SPT on the boundary before gauging, and then.
Well, makes sense. I think right? Okay. If you put some SPD on the boundary and then gauge that, you maybe get some kind of anomalous SCT on the boundary after gauging.
Why is it anomalous?
Sorry.
Why is it anomalous?
Well, its boundary is by definition is anomalous. It has a bulk. After gauging the bulk is non-trivial.
So, but for like if it's a symmetry breaking phase, would you call that anomalous after gauge? If I put a symmetry breaking phase on the boundary and then gauge, will you call that gap boundary anomalous?
Of course, yeah.
Actually, it's quite interesting. The anomaly-free symmetry breaking phase and the anomalous symmetry breaking phase. I think the string fusion may have the same fusion rule, but the F symbol may be different. So there's a such thing as anomalous symmetry breaking phase.
What's the symmetry here? Sorry.
I think here we're talking about the gapped boundary of the SPT phase.
Maybe that is saying if you consider the phase before gauging.
Yeah.
Or I just have a G paramagnet in the bulk, and then I put any G symmetric phase on the boundary. Yeah. After gauging, I should get a boundary for, say, a G gauge theory.
Yeah, that's probably a good way to classify the boundary. And sorry, I don't have really a clear picture for what you could be getting from that.
Right. Yeah, I was just wondering, like, if it's known, like, for each of those phases, what do I need to condense to get that boundary, for example?
The bulk is SPD, right?
The bulk is untwisted. Say it could be twisted, but I'm just considering untwisted.
And the bulk is SPD, and the boundary. If boundary is a symmetry breaking, kind of a canonical boundary, and after gauging, you got this gauge SPD and the boundary where you condense all the particles. But if you start with different symmetric boundary, or maybe symmetry partially breaking boundary, you got some after gauging, that's a mixed condensation. If it's partial symmetry breaking,
right?
Maybe symmetric is correspond to only string condensation.
Any more question? If not, we can thank Tian first. Thank you very much for the lecture.